Hi everyone, welcome to GEMCHEM. Now today's video is on aromatic compounds part 1, and here we are going to deal with aromatic, antiaromatic and non-aromatic compounds. Now before starting, you can watch other videos of organic chemistry. I will give the link in the description box as well as the I button present about this video. And if you are new to GEMCHEM, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first of all, we are going to deal with aromatic compounds, right? So these aromatic compounds are actually very high in stability and has a conjugation effect. And we will deal with these stability using the heat of hydrogenation. So if you look into these datas, that is of hydrogenation, we have one single double bond in this case, which is hydrogenated, and we get a heat of hydrogenation minus 28.6. Similarly, two double bonds which are in conjugation, that is one after the another with one gap in between, provides us the heat of hydrogenation of minus 55.4. Similarly, for this one which is non-conjugated, the energy becomes more. As a result, if we consider when there is three bonds, that is we know this as benzene last one. So here we can see that the calculation shows the energy should be minus 85.8 kilocalorie per mole. But actually it was experimentally obtained that the value was very much less. The value was nearly about minus 49.8 kilocalorie per mole. So why this is so? This gives us the clear picture of the stability of benzene. Due to the presence of excessive conjugation within the ring, there is a resonance energy of benzene, which is near about minus 85.8 minus of minus 49.8, which comes to be as 36 kilocalorie per mole. This is our resonance energy of benzene, and this is the secret of benzene stabilization. Now we have concluded that aromatic compounds are of higher stability and it has a conjugation effect. Easily these heat of hydrogenation can be used to explain the concept, but whatever we are seeing from theory, it is quite different from experiments, as we have already observed in case of benzene. Now we have a question. Is it possible to make the benzene undergo partial catalytic hydrogenation? How? Partial catalytic hydrogenation refers that we have this kind of benzene and we wanted that hydrogen to be given, and it may form two bonds and another leftover bond might have been hydrogenated. So this reaction is our partial hydrogenation. So the question is that, is it possible to do so? Let us see. Now if we plot the same heat of hydrogenation that we have seen in the previous slide in a graph, then we can see that these are the energy levels. If you consider of going from benzene to the previous one having two double bonds, then you can see the reaction needs to be endothermic. And we know that for heat of hydrogenation, this can never be endothermic because the endothermic value is positive, which is never possible. As a result of which, we can conclude that since heat of hydrogenation can never be endothermic, the partial catalytic hydrogenation is not possible. So this is the reaction which is not occurring in the actual situation. Now we will start the main portion of this video, that is identification of aromatic compounds. Now in order to identify the aromatic compounds, what is required? Every identification requires some rules. So for this case we require Huckel's rule. Now Huckel gave an important rule to understand how to distinguish between aromatic compounds and the other compounds. So what did he tell? Let us see. A cyclic, planar and completely conjugated system is said to be aromatic when there is complete delocalization of 4n plus 2 pi electrons all over the center, where n is actually a positive integer. So, first we need to grab the points. First is that the moiety must be cyclic. Second is that the moiety must be planar. That is, it must be in same plane. When this planar can be mostly possible, we know that this planarity can be maximum attained when we have sp2 hybridization. Our moiety becomes planar, right? So, the moiety must be planar, cyclic, as well as it must be completely conjugated system. There should not be any gap between the conjugation. So, these are said to be aromatic. When it has 4n plus 2 pi electrons, what does it mean? If you consider that you have pi electrons 0, then you have 2 electrons, 4n plus 2 gives us 2 electrons. So, a system consisting of 2 electrons, 2 pi electrons to be more specific, is our aromatic compound. Similarly, n equals to 1 is 4n plus 2. If we do, we get 6 pi electron. We know benzene has 6 pi electrons. If you consider, this is 1, this is 2, this is 3. 3 double bonds has 6 pi electrons. As a result, we can conclude that benzene is aromatic in nature. Now we will deal with the next one, that is antiaromatic. Now, if you see that a compound is in closed loop just like the previous case, but the number of pi electrons present in it is 4n instead of 4n plus 2, then we can say that the system is destabilized by 2 electrons, and as a result this is known as anti-aromatic compound. Now, if we deal with the last category, if you consider when the moiety is not planar or not cyclic, then what those compounds are known as? Other than antiaromatic and aromatic compounds, those compounds are known as non-aromatic compounds. Okay, let us see. So, the compounds other than these two types are non-aromatics. So, now we will see different types of compounds and identify what kind of compounds are they, aromatic, antiaromatic or non-aromatic. So, let us start. First, we will deal with this one. So, on looking at this, can you conclude what it will be? First point you can consider is that it is not closed. So, we see that for aromatic and antiaromatic, both should require closing of the ring, but in this case it is not closed. As a result, we can conclude that this is not aromatic, so it is known as non-aromatic, right? Now we will go for the next one, that is cyclopropene radical. If you see here, how many electrons are present? 1 electron from the radical and 2 electrons come from the double bond. So, we have 3 pi electrons. The system is closed and it has double bond in it, but if you consider the number of electrons as 4n or 4n plus 2, it does not match with any of the criteria, right? So, we can conclude that this is non-aromatic. Now, we will deal with cyclopropene cation. So, here we have only 2 pi electrons, right? And these 2 pi electrons shows us that it goes with 4n plus 2, where n equals 0. We can conclude that this is aromatic, right? Now, if you go for the next one, this is a negative, right? And this negative sign always represents 2 electrons. And this is representing 2 electrons. As a result, we have 4 electrons. So, this goes with the formula of 4n, and this is also a closed compound. So, we can conclude that this is anti-aromatic compound. Like this only we can understand what kind of compounds are these, right? So, let us deal with more examples. consider here how many electrons. Let us start. 1 here, 2 here, 2 here. So we have total 5 pi electrons. It does not go with any of the formulas of 4n or 4n plus 2, right? So we can conclude that this is, yes, non-aromatic. Similarly, if we go for the next one, see here, we have 2 electrons here, 2 electrons here. So we have 4 pi electron system. Since there is 4 pi electron system, it goes with the formula of 4n pi, and we can conclude it as anti-aromatic. Now try the next one. Here is 2 electrons, here is 2 electrons, and here is 2 electrons. So tell, what kind of moiety is this? Total number of electrons present is 6 pi electrons. As a result, it comes with 4n plus 2, that is n is considered as 2, and this compound is my aromatic compound. Aromatic compound, right? Now we will deal with the next one, which is this one. So from here you can see that it must be 2 and 2, that is 4 pi electrons, right? Here 4 pi electrons. So we can tell that since there is 4 pi electrons, this one must be anti-aromatic. Now we will see this one. So if you consider this, what must be the answer? See here, you have 1, 2, 3, 4 double bonds. So 4 into 2, that is 8 pi electrons, right? So you must tell that this is anti-aromatic, right? But if you write this as anti-aromatic, you are gone wrong. Why this is so? If you see the actual structure of this 1357 cyclooctatetraene, then you can see that this forms a tub-shaped structure. That is, the structure is not at all planar. It is highly unstable and highly reactive, and it looks like this. And these 2 carbons and these 2 carbons are out of plane. This is actually looking like this, but when we rotate it properly, we can see that these 2 carbons are above the plane. As a result, we will conclude this as non-aromatic. And this is a must case. So this is very important to understand that this is not at all planar, as a result of which it is becoming non-aromatic. Now if we want to make this non-aromatic compound into an aromatic, what we can do? We can just reduce it by an alkali metal to dianion. As a result, it will become planar. So let us see. If we just react it with 2 potassium, use 2 potassium and THF as solvent, then we can see that it forms this compound with 2 dianion. And if we see here, we have 2 electrons. Similarly here 2 pi electrons. For this case also 2 pi electrons. And for the 2 negative charges, it is also 2 pi 2 pi. So we have total 1, 2, 3, 4, 5. 5 into 2, that is 10 pi electrons. And this comes to be as 4n plus 2, which is 4 2s are 8, is my aromatic compound, right? This was a reaction to convert a non-aromatic compound into an aromatic compound. Now we will deal with other few compounds. See here this one. This is known as pentalene. Now if you calculate the pi electrons, 1, 2, 3, 4 double bonds. So there is 4 into 2, that is, it is 8 pi electrons, and this is anti-aromatic. But yes, of course, this anti-aromatic compound can be made aromatic by a simple reaction. If we try to add 2 electrons, then this becomes like somewhat this structure. This becomes this structure, and here we have a negative charge, here we have a negative charge, and this. So if you consider here, now there is 5 into 2, that is 10 pi electrons, and it has become aromatic in nature, right? So this is aromatic. Now we will see another one, that is azulin. This is known as azulin. This is blue colored compound. Now if you see here number of pi electrons, it is 10 pi electron system, and we can say that this is aromatic, right? And it has a strong dipole moment present. If you try this out, if you take this bond here, then this bond opens up, right? And as a result of which we can see that this will look like somewhat this. See here, here the double bond is present, but here negative charge comes, and we have the whole ring like this. This bond has migrated, so here comes a bond, and the others remain as it is, and there is a positive charge. So a dipole moment is being established. This ring has a positive charge, this ring has a negative charge. As a result, the dipole moment is from big ring to the small ring. Strong dipole moment. Next we will deal with another type of compound which is known as anulin. This is known as 10-anulin. How it is written? It is written like this, 10-anulin. Since it contains 10 pi electrons within its ring, it is known as anulin. Now see here, this one is actually non-planar. Why? It has minimal bond angle strain and suffers a severe non-bonded repulsion between the internal hydrogens present. See here, a hydrogen present here and a hydrogen present here. These repel each other. Hydrogen atoms in 1 and 6 position. If you consider this as 1 and this as 6, then there is severe repulsion, as a result of which this interferes and forces some molecules to get out of planarity. And thus we can say that this is non-aromatic. But what happens if we just tie those hydrogens and remove those hydrogens using some other compounds? See here, if we take the same moiety like this and we tie the two ends with one functional group, this functional group can be oxygen or NH or sulfur, and we have double bonds as like previous case, then we can conclude that this has become aromatic. Since there is no two hydrogens present in between 1 and 6 positions, so it is not allowing the molecule to get out of the plane, and we can say that this is aromatic in nature. Okay. Now we will deal with the final thing which is important and already done previously in this channel only, that is Polygon Rule. So this Polygon Rule is already being done in the molecular orbital video. You can watch it. I will give the link in the description box as well as the I button present above this video. I won't repeat this topic as it is already being done. So just we will read out the Polygon Rule, that is the molecular orbital energy diagram of a regular cyclic completely conjugated system takes the same polygonal shape as that of the compound itself, with one of its vertex at the bottom, and the non-bonding line cuts through the middle of the polygon. When all bonding electrons fills the bonding orbitals, then the system is stable and aromatic. The next part, which is our checkpoint. So take a screenshot, try this on your own and let me know in the comment section what is the answer. After watching the video, do write the answers in the comment section so that I can understand whether you have understood or not. Now, so this video was on viewers votes, and in the next video we will also deal with the viewers votes only. So after this video, I will uphold a poll on the community section. So let me know which topic you want to learn. So thank you for watching. Do not forget to like, share, subscribe and comment.